for the organizers for inviting me and for a very nice conference. I really enjoyed it. And yeah, I'm going to talk about algorithms as well, and in particular about distillation and how to compute resonances in Lattice QCD with them. So, wow, this is really high. So for a quick overview, I'll talk about, in general, the challenges of scattering and resonances in Lattice QCD and about the finite volume formalisms. You've seen some of that already in this conference. The main focus of the talk will be how to extract multi-hadron correlation functions from Lattice QCD, which is needed to apply these finite volume formalisms. And then just as an outline, I'll talk a little bit about future projects that could be possible, in this case, B2K star decays. And then, talk a little bit about the code that I was involved in writing for grid and hadrons and conclude. So yeah, I'm going to start with the scattering and resonances in Lattice QCD. And just as a reminder, I mean, it's the last day of the conference, so you're aware, but so Lattice QCD is really successful in computing correlation functions that you can extract stable hadronic states from. So because it's finite volume and Euclidean, if we define a correlation function, it basically behaves like an infinite tower of these kind of exponentially suppressed states. And that means for any stable hadron, we can, given large enough statistics from these correlation functions, extract these kind of finite volume energy levels here, which for a stable hadron, we can then directly compare to experiment once we've done the relevant limits. Exactly, but resonances are slightly different. You can't just simply do this, but there's really rich physics in resonances, and Lattice QCD is really, tackling these challenges now. And I just want to show a little list of things, also partly what we've seen at this conference. So for example, I mean, Luca has really shown these kind of B2 rho decays or B2 pi pi decays, and obviously there's a resonance in it. Then B2K star is another one that's of high interest. Lorenzo has shown these kind of n-to-n pi transitions. And then also, okay, there was a brief mention of K-mixing, but even if you wanted the long distance contribution to this, you would have to tackle intermediate resonances. So it's really important to kind of get a grip on these kind of resonances in Lattice QCD. But if we want to do this, then first we need to control these underlying resonances, which, for example, would be something like the rho resonance or the K-star resonance. And Nelson has given a really nice talk about that for a project that I'm also involved in about the K-pi to K-star scattering. And then, okay, so this is a bit of a different beast, but I'm including it because Shoji talked about it. There's obviously also, for example, charmonium resonances, which are really interesting if you want to really make contact with experiment. And just to repeat, basically from the last slide, so what we cannot have for resonance is to just define a single lattice operator that would couple to the resonance only. So this kind of thing here would be impossible, like it would be for a stable hadronic state. But there is a well-known and well-tested recipe for that, and I'm just going to go through the recipe of how to extract a resonance in Lattice QCD. So what we first need is we need to define a number of states that share the quantum numbers with the resonance we're interested in, and then obtain the finite volume spectrum in that kind of channel. And this talk is about how to do that later. And then once you have that, let's assume that's solved, then there are tools available. There's a finite volume quantization condition, which uses kind of the finite volumeness of Lattice QCD as a tool, so kind of the imprint the finite volume leaves on the finite volume energy levels. That is exploited, so that the volume dependence, to then obtain infinite volume scattering information. And that was, for example, presented by Nelson in the talk. And then, and you could do then what Luca showed with this kind of, so let's say if you extracted pi pi scattering information, this is precisely what Luca did, and then you can do kind of these B2 pi pi decays. Obviously, there's multiple more steps involved, but you can do then computations which go beyond the narrow width approximation, which is how such a decay would have been computed, I don't know, 10 years ago or so, where the rho would have been assumed to be a stable vector state, but now you can really treat it as a resonance if you know all the information from this finite volume state, and you can go beyond uncontrollable systematics, which you would otherwise have. Okay, so this is like basically the same slide, but as a graphical implementation. So this is the full recipe for how you would, for example, in this case, extract pi scattering information. And this is work I've done for my PhD thesis, so it's actually quite old plots. And yeah, Jeremy, who's in the audience, is also involved in this project, or was. So yeah, first you define your finite volume states. In this case, you have rho vector states, and you have pi 2 hadron states, or interpolators. And then you construct a matrix of all the possible cross-correlation functions of these states, all the states in your system. And yeah, I called this a rho. I mean, beforehand I made a point that there is no such thing, but I just gave it this letter. And once you have this matrix, then you can, we've seen this often in this conference, you can solve a GEVP on that, and then the eigenvalues you get from the GEVP, they should give you a nice like tower of states in the spectrum. So you could plot this, for example, like an effective mass like here, and then you get your finite volume energy states. For this particular matrix here, there will be one such matrix for each momentum frame and the irreducible representations you have in these momentum frames. But yeah, and then this finite volume formalism, which I mentioned beforehand, would give you a map that tells you if you have this state down here, that will precisely predict you the infinite volume phase shift for that given energy. So what's on the y-axis here would be on the x-axis here, and it will give you the finite volume phase shift data for that particular point. And you can use all the energy levels you extracted to kind of put these in these plots. The red line here is in this case, 4 pion threshold on that particular ensemble, because strictly speaking, the formalism isn't applicable anymore above kind of when that threshold's opened up, because we don't have a formalism for 4 particles yet. Okay, and this is just a little animation. I mean, I'm basically showing exactly the same plot as beforehand. So this is like one particular frame and irreducible representation. In this case, the rest frame and the T1 representation. And like before, each of these energy levels corresponds to one of these data points. And then for the same scattering process, I have, for example, in a moving frame, have additional energy levels, and then they would map to these kind of green points here. And then you can, by studying multiple frames, you can keep going, and you can really see how this kind of phase shift curve is forming, and how you can really see the phase shift crossing pi half, and you can really see the imprint of a resonance here. And then perform a fit to that, in this case a Breit-Wigner. And yeah, as I said, this is the work I've done in my PhD. Exactly, so this is for the rho resonance at some pion mass of 300 MeV. Okay, so as further motivation, I just wanted to show some of the things I liked in this conference. So these are slides from Tom Blum, where I was talking about the G-2, and this is all about projects which don't necessarily use distillation. I mean, this one does, but yeah, definitely profit from this kind of finite volume formalism, etc. So you can see here a very similar slide which Tom showed, where like to get the long distance contribution to G-2, you can also extract in the rho channel this kind of tower of finite volume states, and then you can reconstruct the vector-vector correlator for the long distance, which dramatically improves the precision you have there, which really like helps the precision calculation of the G-2. Yeah, and then another example, I talked about that already, and I'm involved in this project as well, but Nelson studied the K-star resonance, or K-pi scattering. And yeah, what I really like about this work is that Nelson really assigned not only a statistical error with this fit, like I've shown before, but like really went to get a grasp on the systematic error by doing this kind of AIC-driven sampling method, sampling 50,000, because it's unclear when you see these kind of effective masses or correlation functions here, which fit would be like the perfect one. And then you have this two-step analysis where you fit your energy levels first, and then you feed them into the finite volume formalism. And it's kind of very non-trivial how the final result will change if you would have fed in a different fit into the final thing. So yeah, Nelson has really done these kind of 50,000 samples here of different fit ranges on the left-hand side, which were like sampled with an IRC criterion, and then was able to assign, as you can see in these histograms for the coupling and the mass, a systematic error for these kind of for the phase shift here. And then also there was Lorenzo's work where n-pi scattering was shown also then to be with the kind of n-gamma to n-pi transition. And also here, I don't think this work used distillation, but you can really see how there was also GVP used, because not only nucleon 3-point functions were used, but then also the n-pi 3-point functions. And Lorenzo really impressively showed how you can really improve the overlap or the plateau you can get in these ratios just by solving the GVP and by getting a better overlap with the state you're actually interested in. And then the final thing I have from this conference is Luca's slides where, so the B to rho transition was basically computed. So in addition to the pi-pi scattering, you then have to look at these residues here in the 3-point functions, and then Luca has this really nice plot of the B to rho LNU transition period. Okay, so much for motivation for why scattering in lattice QCD is interesting, and why, we're in principle interested in using these techniques. There's really nice physics that comes out of it. And now, I want to talk about how to do that, and in particular, how to get these kind of multi-hadron correlation functions from lattice QCD efficiently. And that would be using distillation in this talk. So, okay, so just to take a step back again, as I said, all this nice physics, which I showed before, you can basically obtain in lattice QCD if you, and the first step to do that, or one of the early steps, is that you need to kind of define or kind of compute a correlation function matrix like this here. And the example I'm doing here is again for k-pi scattering. I mean, if you have a different system like nucleon pi scattering, obviously you define a different matrix. But importantly, you define your interpolators, in this case, in the k-star channel. So that means you have a k-star interpolator, you have multiple k-pi interpolators, and then you can define a matrix like this from this. And the question is now, how do we compute this efficiently? And one of the difficulties in that is that you will have correlation functions like this one here, which basically has 4 mesons involved in it. So you have a k-pi operator at some times less t, and you have a k-pi operator at some times less t0, and they all have individual momenta, and you want to project each meson into definite momentum to get a good overlap with the spectrum. And this correlation function for this, you, for example, would need to compute a Wick contraction like this one here, where all the mesons are connected with each other, and in particular, if you want an estimator for these on every single time slice on your lattice, then this will include an all-to-all propagator. So one of the time slices you can always get away with translation and invariance, but if you have this this box here, then you always have an all-to-all propagator, which is just difficult to estimate. Exactly, and this is where distillation comes in, and it's a by now fairly old idea, but it's extremely successful. So the first kind of proposal comes from this paper from 2009 here, and it's still being used very heavily, and I would argue that it really revolutionized the field of scattering in lattice QCD. And the idea is that you start from the 3D lattice Laplacian, and that you compute the eigenmodes of that Laplacian, which are the eigenvectors v and the eigenvalues, which are called lambda here. And then you define this kind of distillation operator, which is basically constructed from the eigenvectors and kind of a sum over the eigenvectors here. But there's a cutoff in the number of eigenmodes you use to construct this, which I call NV here. And then this, and in matrix notation, you can write this succinctly as kind of v Decker, where each v kind of is a vector that includes all these kind of eigenvectors itself. And then you can use this matrix as a quark smearing matrix. So all the quark fields you then redefine as a smeared quark field with this particular smearing matrix with the distillation operator. And then when you do this, what happens is that your propagator, which is just this product of quark fields here, that will be smeared on both sides. So you have a smearing applied here and a smearing applied here. And the smearing expand in this matrix notation in this VV dagger, into this VV dagger thing. And then the key kind of observation here is that this center bit, this V dagger times propagator times V, that can basically be defined as, well, it's an important object in the formalism, and it's typically called a perambulator, this tau. And it's basically the Dirac operator projected into the lowest eigenmodes, into these NV eigenmodes of the lattice Laplacian. And what this means in practice is that the Dirac operator, which is a matrix that's kind of the size like of lattice size, like a matrix with each dimension like the length of the lattice size, that is reduced to the number of eigenvectors here, which is dramatically smaller. So, for example, I mean, we've seen that even a moderate, or like this is a large, but not the largest lattice that's been used. Even if you have a lattice size of 48 in spatial direction, and this is the example from the work that Nelson presented, and then you compare this L cubed to the number of eigenvectors you use. I mean, in this work, 60 was used, and yeah, I mean, there was a comment at this conference that this might be at the lower side, but even if you would not use 60, but 600 or whatever, even 6,000, you get a drastic reduction in the size of this kind of matrix up here. So in this particular case, which are the kind of parameters for the work that Nelson presented, there was a reduction in 10 to the 6th. And these eigenvectors here, these V's, they're fairly cheap to recompute. So once that means that you can store this object, this tau here, you can actually store it on disk. It becomes feasible to kind of store it on disk or in memory or wherever. And then anytime you want access to the full propagator, you can just recompute these eigenvectors here of the lattice Laplacian and can reconstruct your propagator and then use it for the rest of the formalism. And the other thing this leads to, and this is also very crucial, is that the propagator actually factorizes into two pieces. So into one that's, so the propagator has like two spatial indices, so it's from one lattice point to another, but it really factorizes into one piece that's purely on one of the lattice sides and one piece that's purely on the other of the lattice sides. And then once you have this factorization, this is not just about distillation. Or these kind of identities are for any theory where you have or for any formalism where you have the propagator factorizing. Then you can form, for example, for an endpoint meson function, you can factorize it into these kind of so-called meson fields. So, I mean, maybe that's a bit much to pass, but you can just reorganize your quark fields here so that once you write them as this kind of factorized propagator, you can group them as kind of one part of the factorization with the gamma insertion and the other part of the factorization, and this whole object will just be defined on a single lattice side. And then you could, in this case, Fourier transform it into definite momentum, and that would tell you that this endpoint mesonic function here could be written as a trace of a product of n of these meson fields, each of which are projected to definite momentum and are defined at a specific time and have like a Dirac insertion here. Okay, some more details. I mean, distillation has been expanded, but this is all a fairly old idea into stochastic distillation, I would call it. So dilution is used. So you use dilution projectors where you can, which dilute in the number of eigenmodes you have in the spin degrees of freedom, and in time you could also use dilution. And that's basically just an additional insertion here in addition to these perambulators, which are defined on the last slide. And then you can stochastically sample this with these kind of noise vectors eta here. And then you still have this, and then you get these kind of functions phi and rho. Yeah, so it's an advantage that you can sample stochastically. I mean, for what I will be talking about, the only crucial and important thing is that we still get a factorization of the propagator. So just like before, where like we had this product, basically the propagator factorizes in a piece that's only dependent on x and another piece that's only dependent on y. And then you can still do this meson field approach, and a meson field at definite momentum would be defined as this Fourier transform of this kind of rho field with a gamma insertion in the y field. But yeah, the advantage is you could then sample stochastically in the number of modes, for example. Okay, so to go back to the k-pi scattering thing, so there's, or like to any kind of mesonic 2-to-2 scattering, there's like, if you look at a selection of diagrams which you have to compute, would be all these, and each of the blobs in this kind of diagrammatic representation would correspond to a single meson field. So this one here would be one of these meson fields with a rho and a phi. This would also be a meson field with a rho and a phi, and so on. And you can see quite nicely from this illustration already that once you've computed these meson fields, and again, they're not super small, but they're fairly small because they don't scale with the size of the lattice, but with the size of these eigenmodes, they're feasible to store on disk at least in like intermediary for like the length of the running of your project, but you could really store these, and then you can assemble all these different correlation functions because you compute each of these meson fields first, and then you can imagine that if once you've computed everything for this diagram here, then you already have this in this blob, and you could reuse the same meson fields to compute this diagram as well. So you can really profit from reusing this. And this is exactly what we want, because we want to compute this kind of large matrix of all these kind of cross correlations. And yeah, for example, I mean, okay, this is just writing out the middle diagram again, because beforehand I had an endpoint function. But if you think of like this kind of 3-point function here, I mean, I call this a 3-point function. It's now a 2-point function with 2 mesons and 1 time slice. And you think of it as at momentum 0, you would just need this vector meson field here at momentum 0 and time slice t1, and then you have 2 meson fields which are at the same time slice and opposing momenta, and then you could just assemble these correlation functions from these particular 3 meson fields. Yeah. Okay, so just as a summary, why I think distillation is so well suited for scattering. I mean, the most important for me, I think, is the factorization. Due to the factorization, we can project into the momenta and Dirac matrices after doing the inversions, which is typically what's dominating the cost in a lattice simulation. So once we have a large operator basis, we really profit from reusing these kind of costly inversions. And then, yeah, you can, I mean, there's like it's fairly expensive to kind of employ the formalism, but you really profit if you want to compute a lot of correlation functions, which is precisely what we want. And then also, yeah, we can, yeah, that's what I was just saying. And then you can, if you want to, like, treat distillation stochastically, that's been very successfully applied. I mean, this is a very technical comment, but yeah, there's one extra thing that you then have to also think about. Because you apply noise vectors to each of the diagrams, you will have to use one independent noise vector per quark line that enters your diagram. So there is also an additional cost which comes in the stochastic distillation. So while this one here would need a minimum of 2 independent noise vectors to avoid bias in the sampling, this diagram on the right would already need 4. So it's not that stochastic distillation is just cheaper. There's also something you have to invest. Okay, and also I think quite crucially, the inversions which are projected into this distillation subspace, so the perambulators, they can be stored really quite cheaply. So even if you want to use them for another project later, you wouldn't have to redo your inversions, but you could really just use what you have already. And yeah, so far I only talked about mesons, but even if you have a mesonic project, you could really profit from that if you do a baryonic project, for example, because you would just equally could define a baryon field and then use the same inversions you have used already beforehand. Okay, so just briefly, I want to talk about some ideas and developments that I like. which go beyond these kind of, I would call them the first ideas of distillation. I mean, what I showed so far is ideas published in 2009 and 2011. So there's been this paper recently where to do distillation at high momentum, this very successful momentum smearing was implemented into distillation. And on the right, you could see the result, which they saw where on the top, so these are effective energies for the nucleon, and on the top is basically standard distillation, like I explained it before, as far as I understand it. And then at the bottom, you can see for the same system with, I believe, comparable costs or statistics, the effective energies when you use this momentum smearing. And you can really see better overlap, in particular, if you go to higher and higher momentum, where, like, typically correlation functions would get very noisy. And that can be really interesting if you want to do distillation at high momentum. And then also recently, there's been this publication, which I also find very exciting, about the optimization of meson profiles. So here the smearing matrix, which is kind of this VV dagger thing, gets a smearing profile inserted inside it. So if I would just set the smearing profile J to 1, I would just have standard distillation like I showed before. But you can, or in this paper they showed that you can construct an optimized smearing kernel by solving the GVP, I believe, of standard distillation first, and then looking at the Gaussian quark smearing profile, and then you can optimize this smearing profile here. And then in this one exploratory study, this is a fairly recent work, where they could really see that for quark masses at half the charm quark mass, they really saw an improved overlap with the states in the spectrum. So on the right-hand side, you would see, I believe in blue, this is not using distillation at all, that's just stochastic estimators. But then black is, so standard distillation like I showed it before, and like I talk about in this talk here mostly. But then in red, you can really see how the overlap is improved with these kind of smearing profiles. So the plateaus, the onset to the plateaus is much earlier than the black ones. So these are like two ideas which I find exciting about new developments here. Okay, and then how am I doing for time? I still have 15 minutes? Yeah, okay. So very good. So this is everything I wanted to talk about distillation in general. I just want to outline a strategy now, how one could tackle an interesting process. In this example, B2K study case, this is kind of similar in some regards to what Luca has shown. But yeah, I just in general maybe want to show that, so all this resonance information, they can be used for multiple things, all of which are like very exciting in Lattice QCD. And there's really an abundance of things that one could study. I mean, first of all, you could just study these kind of benchmark resonances like the pi and k-pi scattering. But to go beyond that and to go like to experiments that are being performed maybe now, I mean, BDKs are interesting. Beta rho and B2K star, you could do these electroweak transitions into resonant states. An easier, not easy, but easier warm-up exercise that's been done are these kind of 1 to 2 transitions, pi gamma to pi pi, k gamma to k pi. I grouped it down here, but Lorenzo has shown the same in kind of baryonic channels with n gamma to n pi. I mean, you could think about weak transitions with 4 quark vertices. They would be very hard to tackle because you would need your individual field for this kind of 4 quark vertex. So I don't know whether that's feasible, but it is physics involving resonances, so that's kind of worthwhile thinking about. And then, there are formalisms as well already for 3 particle scattering. They are like a lot more complicated than the 2 particle ones are, but also a lot less has been done. So that's also a very exciting avenue to go into. And so what I want to talk about is these kind of electroweak transitions. I'm not going to talk about the other ones. And Nelson has covered kind of these underlying benchmark resonances a little bit. And so there's been some pioneering work for the formalism for these 1 to 2 transitions. I mean, I just linked all these publications here. If you're interested, you can open my slides and click on them. But both for the pi gamma to pi pi and k gamma k pi, there have been several publications already where kind of it was shown that distillation can really control these 1 to 2 transitions. But then obviously there are kind of these processes which are of very high interest because also there's kind of B anomalies and they're measured at LCB right now. And yeah, the only one I'm really aware of which treats it fully is Luca's work, which was presented at this conference here. And just to like mix things up a bit, I wanted to like go into how one would do this with a K star instead of a rho, and then because it's a B2S transition, you have an L plus L minus and not an L nu, but it's similar. So I want to give an outline of how to compute these correlation functions. So first of all, you need to modify distillation a little bit, because if you remember, the projection in distillation inherently includes this kind of smearing operator. So the smearing is part of how the whole formalism works. So the whole benefit of profiting from the smaller bases comes from smearing the quark field. But what we want for an electroweak transition is we want local matrix element insertions here. And the good news is there is a possibility you can extend the formalism to allow this. You can define local quark fields by simply not smearing one of the 2 fields in the propagator. And then you have these kind of new fields phi here, which are basically just an inversion on one of the vectors. The disadvantage you get is that you also lose the benefits of distillation. You can't just cheaply store these objects anymore. They're very large, and there's no other way to kind of use these. But in principle, you can compute all these diagrams also with a local insertion. What you couldn't do is you couldn't do a 4-point function. This is maybe just an aside, but like Shoji has talked about these kind of inclusive decays where you need 2 local insertions, and you cannot have a local to local transition within distillation. You could compute the quark line with a different formalism, but yeah, basically by using gamma 5 hermeticity, we can turn around these kind of propagators here, and then we have a fully local insertion at one of the points, which is exactly what we want for an electroweak transition. And then the strategy, what you want to do is you compute all the kind of 2-point functions, the 1 to 2 and 2 to 2 ones, like I explained before. And then you also compute your 3-point functions where, due to the gamma 5 hermeticity and the smearing, you have to like have one field at the time slice. Well, in this case, at the time slice of the B meson, you have one field at the time slice of the K star or K pi insertion here. And then the local field in the middle is the one which you can keep variable. There's no really a choice in the time variable because there's gamma 5 hermeticity, which is kind of needed to do the local insertion. That kind of demands that also this one will be the field that you can vary in the final in the estimation of the 3-point functions. So the 3-point function you will get out will be like at a particular time slice TB, at a particular time slice TK pi, and then you get out a correlation function for all the time slices of the current insertion. Okay, and then what you can do, you can solve the GVP like we've done before. This is exactly the same thing as in for the 2-2 scattering. And then as opposed to using the eigenvalues, which beforehand I've always used to show these kind of effective mass plots of the GVP, you can use another part of the GVP, which are the eigenvectors. This is actually quite similar to what Thomas talked about in the G-2. And then you define these optimized interpolators here, where like now, with a little more confidence, I'm giving this a superscript of K star, because now I really have a linear combination of all the operators or interpolators put into the system, and the GVP tells me that the state which is where I expect the K star resonance, that what the eigenvectors tell me how much of each operator should contribute to this particular state. And this is, yeah, this will be then an optimized operator which I get for the K star resonance, and then I can use this linear combination here to then, when I have the 3-point functions for each individual operator in the system, I can then basically define my 3-point function where, with the K star operator, which is a linear combination of these kind of 3-point functions with the particular states. So this is what I mean with this kind of optimized overlap operator. And having this 3-point function then would allow to get these kind of matrix elements here, which would really be the matrix element of a B with this kind of electromagnetic transition into a K star. And that would be beyond the narrow width approximation. This is really what one would be interested in to study these decays. And yeah, they have been studied on the lattice, but only with using this narrow width approximation. And it's really interesting for experiment to go beyond that, or for like comparison with experiment. Okay. I'm not going to get to the last point. Okay, so just to show that, so this was a short recipe to say this is how you get the correlation functions, but also I just want to highlight this. Thank you. Yeah. There's a lot of challenges that go far beyond just computing correlation functions. So I'm just outlining here, this is the LHCb plot, the latest one. No, it's not the latest one. It's from 2017 is the latest one for B2K style plus and minus decays. And you can see the data points in black here as a function of Q squared for this kind of branching fraction. And in blue, you can see the theory prediction, where for large Q squared, that comes from lattice QCD. And as I said, this is using the narrow width approximation. And at small Q squared, this is from dispersive methods. And you can see that kind of what people talk about when they say the B anomalies, then one of the B anomalies, and interestingly, one of the ones which, at least to my knowledge, really hasn't gone away with kind of the recent publications, is that for many of the semi-leptonic B decays, the theory prediction is higher at low Q squared than the experimental values. So it would be quite interesting. So ideally, what we would want to do is we would have a lattice computation in this kind of region for these B2K star form factors from which one could then get these transition amplitudes. But this is not so easy, or almost impossible, I would say, with current techniques. And I just want to outline why. So the reason is that lattice is actually really best at Q squared max, where like both the B and the K star are at rest. I mean, we can give some momentum to them. Ideally, we want to give it to the K star just because it's much lighter, and that will have a larger effect on the Q squared. If we give it to the B, it's not going to be a very large effect. But because we deal with a resonance, this is a little bit harder. So I just did a quick calculation, again, with the lattice from Nelson's talk. So if we wanted like the dream calculation at the physical point with physical light and heavy quark masses, then just because the B is just so heavy, you would need ridiculous or impossible momenta to give to this K star or B to reach, well, Q squared 0, but even something down here would be really hard. I mean, I'm not suggesting that anyone computes stuff with momenta like these. This is basically to outline just how impossible it is to reach this region. And very importantly, you might remember from earlier on that I said the formalism breaks down once you exceed certain thresholds. And even what we would do if this was a B2K L plus L minus transition, we would like to give a lot of momentum to the K, and we could get away with it, but with the resonance, we also exceed all these channels, the multiple particle channels, and therefore also we don't really know how to apply the formalism here. And then also, I mean, Shoji talked about these germanium resonances in between. I mean, in his talk, they were kind of vertical bands here, and here it's just, they just don't plot the data here because they don't trust the data in that region, but there are these two germanium resonances here, the psi2s and the j-psi. And yeah, Shoji really said that one needs to be cautious if one wants to go below these, because it's absolutely not clear that if you have, like, that we know what goes on in here, or that we can easily go to these small Q squared and just, it's hard to assign a systematic error to that, and there will be a systematic error to it. So in summary, it's just still very challenging. So with the current techniques which we have and which I showed, I mean, this is an open question whether one can calculate these, but any calculation, I think, that is kind of can be done in the foreseeable future with current techniques would need slightly unphysical kinematics, so like larger than physical light quark masses, much lighter than physical B quark masses, or has to be restricted to larger, very large Q squared. Okay, very good. How many minutes do I have? A little bit. I'm just going to advertise. I mean, Raul is going to talk about this next, but I'm just going to advertise that there's this grid and hadrons code, which I helped develop. Nelson, who's in the audience, also developed quite a lot of it. But there is some distillation code available there. It's in hadrons. It profits from everything that's in grid, which means that it runs on GPUs, architecture agnostic. Well, we'll talk about this in the next talk after the coffee break. But yeah, if you want to use this, that's available. Talk to me if you want to use this. These are all links. You can click them. They are for links to get started with hadrons. Or we made some example workflows for distillation where you can see how you would set up a workflow. And yeah, everything to compile this and use this should be in here. But yeah, stick around for the next talk. Okay, so to conclude, so I talked about distillation and well, basically the motivation was that we have finite volume formalisms that allow us to study infinite volume resonance properties if we have a correlation matrix of operators with precise spectrum overlap. And what I talked about is how we can get such a correlation matrix, and in particular using distillation as a technique. There is this grid and hadrons code available, which has stochastic and exact distillation implemented. The rest Raul will talk about. Importantly, it's free and open source, so you can really just use it. And this, crucially, is the first step towards studying anything of the exciting physics project that I talked about here. And then I talked a little about these electroweak transitions into resonances, and for that you need 3-point functions with local insertions. They can be computed within distillation. So actually, there, I would say more of the challenge is not in the computation of the functions. That's basically solved, whatever that means. But it's more in that we really need to understand the formalisms to actually find corners where we can do meaningful comparisons with experiment. And the grid and hadrons code is ready. There are some things which are still on the wish list, not in there. If you want to get involved, talk to me. It's free and open source code, and it would be exciting to get more people interested. And that's everything I have.